Welcome back. The determinant is often taught as a formula to memorize, multiply this, subtract that, but underneath the arithmetic is one of the most vivid pictures in linear algebra. The determinant measures area and volume. For a 2x2 matrix, it is the signed area of the parallelogram the matrix builds from the unit square. For a 3x3 matrix, it is the signed volume of the box the matrix builds from the unit cube. More than that, a matrix scales the area or volume of any region by the absolute value of its determinant. That one idea explains the determinant's whole reputation. When it is 0, space has collapsed and the matrix cannot be inverted. When it is negative, orientation has flipped, like a mirror. Today, we build the determinant straight out of area and volume, derive the 2x2 and 3x3 formulas as the natural consequence, and read invertibility and orientation right off the geometry. Start in 2 dimensions. Picture the unit square, the little square with corners at the origin, and the 2 standard unit vectors. A matrix transforms that square, and because the matrix acts by sending the first unit vector to its first column and the second unit vector to its second column, the square becomes the parallelogram spanned by those 2 columns. For a matrix with first column AC and second column BD, the area of that parallelogram works out to a times D minus B times C, and that is exactly the determinant. So the 2x2 formula, AD minus BC, is not arbitrary at all. It is the area of the parallelogram the matrix creates. We call it the signed area because it carries a sign. If the 2 columns preserve the usual counterclockwise orientation, the determinant is positive. If they swap that orientation, it comes out negative. Strip the sign away with absolute value and you have the plain geometric area. The same story lifts to 3 dimensions. Now the relevant region is the unit cube, and a 3x3 matrix transforms it into a parallelepiped, a slanted box spanned by the 3 columns of the matrix. The signed volume of that box is the determinant. There is a neat way to compute it. If the columns are the vectors u, v, and w, then the determinant equals the scalar triple product, u dotted with the cross product of v and w, which is the quantity we met back in the geometry episodes. The absolute value of the determinant is the box's volume. The sign again records orientation. A positive determinant means the 3 columns form a right-handed system, keeping the orientation of space, while a negative determinant means a left-handed system, a flip. And if the determinant is 0, the box has been flattened. Its 3 columns lie in a common plane, so it has no volume at all. Here is the idea that makes the determinant powerful rather than just cute. The determinant is not merely the area of the one parallelogram you get from the unit square, it is the scaling factor for the whole transformation. Take any region in the plane of any shape and apply the matrix, its area gets multiplied by the absolute value of the determinant. A region twice as big, a circle, a blob, every one of them has its area scaled by the same factor. In 3 dimensions, the same statement holds for volume. This is why the determinant deserves a single number. It captures how the transformation stretches space, uniformly everywhere. One beautiful consequence is multiplicativity. If you apply one matrix and then another, the area scalings simply multiply, which means the determinant of a product equals the product of the determinants. 2 stretches in a row compose into a single stretch whose factor is the product. The geometry makes that algebraic rule feel inevitable. The most important special value is 0. When the determinant is 0, the geometry collapses. In 2 dimensions, the parallelogram has 0 area, which happens when the 2 columns are parallel. The unit square gets squashed flat onto a single line segment. In 3 dimensions, the box has 0 volume, which happens when the 3 columns all lie in one plane. The cube gets flattened into a sheet. In both cases, dimension has been lost. And once dimension is lost, the transformation cannot be reversed, because many distinct starting points get crushed onto the same image point, and you can no longer tell which one you came from. So, the determinant being 0 is exactly the condition for the matrix to be singular, not invertible, which is also exactly when the rank is less than the full size of the matrix. This ties together 3 threads from the course. The determinant, invertibility, and rank all agree. The determinant is, at heart, an invertibility detector you can compute. We keep saying signed area and signed volume. Let's make the sign concrete. The sign of the determinant tells you whether the transformation preserves or reverses orientation. When the determinant is positive, orientation is preserved, right stays right, and a counterclockwise loop stays counterclockwise. When the determinant is negative, orientation is reversed. Like looking in a mirror, a right hand comes out as a left hand. A clean example is reflection across the x-axis, the matrix with first row 1, 0, and second row 0, -1. Its determinant is -1. The absolute value is 1, so areas keep their size. A reflection does not stretch or shrink anything. But the sign is negative, which signals that orientation has been flipped. That is the entire content of the minus sign, same area, mirrored world. The magnitude measures how much space stretches. The sign measures whether space gets turned over. Here is the picture the whole episode rests on. On the left is the unit square, sitting on the grid with the two standard unit vectors along its edges, and its area is 1. The gold arrow in the middle is the matrix A doing its work. On the right is the result. The two unit vectors have moved to the two columns of A, and the square has become the parallelogram they span. The area of that parallelogram is the determinant, AD minus BC, so the determinant is literally the area the unit square grows or shrinks to. The little curved arrow inside each shape shows orientation. Here, it stays counterclockwise in both, so the determinant is positive. And down in the faded inset is the degenerate case. When the two image arrows point along the same line, the parallelogram flattens to a segment, the area is 0, and the determinant is 0. One figure holds area, orientation, and collapse all at once. Here is the three-dimensional version of the same picture. On the left is the unit cube, anchored at the origin with its edges along the three standard unit vectors, and its volume is 1. The gold arrow is the matrix A transforming it. On the right, the three unit vectors have moved to the three columns of A, and the cube has become the parallelepiped, the slanted box, that those columns span. The volume of that box is the determinant. The small right-hand crow near the box signals that the three columns form a right-handed system, so the determinant is positive and orientation is preserved. Down in the faded inset is the collapse. When the three image arrows all lie in one common plane, the box flattens into a sheet, its volume drops to 0, and the determinant is 0. So in 2 dimensions, the determinant is the area a square grows to, and in 3 dimensions, it is the volume a cube grows to. The very same idea, 1 dimension higher. Before we compute a 3x3, here is the recipe in general. To evaluate a determinant of size 3 or larger, you expand along any single row or column. First lay down the checkerboard of signs, plus in the top left corner, then alternating plus and minus across and down. For each entry in your chosen row, you form 3 things: the entry itself, its checkerboard sign, and its minor. The smaller determinant you get by crossing out that entry's whole row and column. Multiply those together for each entry and add the results. That sum is the determinant. The practical tip that saves enormous effort is to expand along whichever row or column has the most zeros, because every 0 entry kills its entire term before you compute anything. A row with 2 zeros turns a 3-term calculation into a single term. We will use exactly that trick in the worked example coming up, expanding along a top row that happens to carry a convenient 0. Let's compute one. Take the matrix with first row 3, 1 and second row 1, 2. The 2x2 determinant is the top left times the bottom right minus the top right times the bottom left. 3 times 2 minus 1 times 1, which is 6 minus 1, or 5. What does 5 mean? The unit square maps to the parallelogram spanned by the columns 3, 1, and 1, 2, and that parallelogram has area 5. More broadly, this matrix multiplies the area of every region by 5. Because the determinant is positive, orientation is preserved, and because it is not 0, the matrix is invertible. For contrast, look at the matrix with first row 2, 4 and second row 1, 2. Its determinant is 2 times 2 minus 4 times 1, which is 4 minus 4, 0. Here the columns 2, 1, and 4, 2 are parallel. The second is just double the first, so the parallelogram collapses to a line and the matrix is singular. Same formula, opposite fate. Now, a 3x3. Take the matrix with rows 2, 0, 1, then 3, 1, 2, then 1, 0, 4. We expand along the top row using the checkerboard signs plus, minus, plus. The first entry is 2, multiplied by the determinant of the little 2x2 you get by deleting its row and column. That block is 1, 2 over 0, 4, with determinant 1 times 4 minus 2 times 0, which is 4. So the first term is 2 times 4, 8. The second entry on top is 0, so its whole term vanishes. A nice reason to expand along a row with zeros. The third entry is 1, with a plus sign, multiplied by the determinant of the block 3, 1 over 1, 0, which is 3 times 0 minus 1 times 1, or negative 1. So the third term is 1 times negative 1. Adding up, 8 minus 1, which is 7. Geometrically, the unit cube maps to a box of volume 7. Since 7 is not 0, the box is not flat and the matrix is invertible. Since it is positive, orientation is preserved. Let's see a determinant come out 0 and read the geometry from it. Take the matrix with rows 1, 2, 3, then 2, 4, 6, then 0, 1, 5. Notice the second row is exactly twice the first. The rows are dependent. Expand along the first column. The first entry is 1 times the minor 20 minus 6, which is 14. The second entry is 2 with the minus sign times the minor 10 minus 3, which is 7, giving minus 14. The third entry in the column is 0, so its term vanishes. Adding 14 minus 14 is 0. The determinant is 0, and the reason is geometric, because the columns are dependent, they all lie in a single plane, so the parallelepiped they would span is completely flat, with 0 volume. A 0 determinant tells us the matrix is singular, it has no inverse, and its rank is less than 3. The transformation crushes all of three-dimensional space down onto a plane, and once that dimension is gone, no inverse can recover it. Several matrices give up their determinant with no work at all, and these shortcuts are worth memorizing. For a triangular matrix, upper or lower, the determinant is simply the product of the diagonal entries. Everything off the diagonal is irrelevant. The identity matrix has determinant 1, which fits the geometry perfectly. It leaves the unit cube exactly as it is, volume 1. Any matrix with a row or column of all zeros has determinant 0 because the box collapses. Any matrix with 2 equal rows or 2 proportional rows also has determinant 0 since those directions are dependent and the box is flat. And scaling one row by a factor scales the determinant by that same factor, which means scaling the whole n by n matrix by k multiplies the determinant by k to the n. This last family of facts is exactly why elimination computes determinants in practice. Reduce the matrix to triangular form, multiply the pivots, and flip the sign once for each row swap you made along the way. A little history. Determinants were discovered independently in the late 1600s by the Japanese mathematician Seki Takakazu and, in Europe, by Gottfried Wilhelm Leibniz, who described them in a letter while studying systems of equations. In 1750, Gabriel Cramer published the rule that bears his name, solving a linear system using ratios of determinants. We will see exactly that next episode. In 1771, Alexandre Théophile Vandermonde was the first to treat the determinant as an object worth studying on its own, and a particular determinant still carries his name. The modern theory came in the 1800s with Augustin Louis Cauchy and Carl Jacobi, who established the multiplication rule, fixed the very word determinant, and introduced the Jacobian, the determinant that governs how areas and volumes change under a substitution in calculus, exactly the scaling factor idea from today, applied to curved maps. Let's recap. For a 2x2 matrix, the determinant is AD minus BC, and geometrically it is the signed area of the parallelogram the matrix makes from the unit square. For a 3x3 matrix, the determinant is the signed volume of the box the matrix makes from the unit cube, and you can compute it by cofactor expansion along a convenient row, ideally one with zeros. The determinant is the scaling factor of the whole transformation. It multiplies every area or volume by its absolute value, and the determinant of the product is the product of the determinants. When the determinant is 0, space has collapsed to a lower dimension, so the matrix is singular, not invertible, with rank below full. And the sign carries orientation. A positive determinant preserves the handedness of space. A -1 flips it like a mirror. Next episode, we collect the algebraic properties of the determinant and put them to work with Cramer's rule. Today we found the geometry hiding inside the determinant. A 2x2 matrix turns the unit square into a parallelogram, and the determinant of the matrix is the signed area of that parallelogram. A 3x3 matrix turns the unit cube into a slanted box, a parallelepiped, and the determinant is its signed volume. So a matrix scales every area or volume by the absolute value of its determinant. That single factor applies to any region you start with, not just the square or the cube. The word signed matters. When the determinant is positive, the transformation preserves orientation. It keeps the handedness of space. When it is negative, the transformation flips orientation, like a mirror reflection. And when the determinant is exactly 0, the parallelogram has collapsed onto a line, or the box has been flattened into a plane, the transformation has crushed space into a lower dimension. That is precisely when the matrix is singular and cannot be inverted, because once dimension is lost, there is no way to undo the collapse. We met the formulas too, for a 2x2, AD minus BC, for a 3x3, the cofactor expansion along the top row. Next episode, we gather the algebraic properties of the determinant and put them to work with Cramer's rule. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.